Hi, good afternoon, everyone. We'll go ahead and get started. My name is Meta Polywell with the Orange County Water District, and I'm really excited to welcome you all to our webinar today. Our speakers from the Orange County Water District and the City of Santa Monica will share their experiences with enhanced recovery reverse osmosis technologies for potable reuse and brackish groundwater treatment. Before we get started, I do want to mention that we are in webinar mode, so attendees are muted to reduce background noise. The webinar is being recorded and will be published on the OCWD YouTube channel. And lastly, we'll take questions at the end of our presentation, so we encourage you to submit your questions in the Q&A box. We'll do our best to get to as many questions as we can today and address questions most relevant to the information presented here today. Now, with that, I would like to introduce our speakers. Dr. Han Gu is a senior scientist and process specialist in the Research and Development Department at the Orange County Water District. He has earned his degrees in chemical engineering from UCLA and has 9 years of research experience. Han specializes in membrane-based treatment technologies and focuses on pilot testing to optimize advanced treatment processes for potable reuse. Han also leads projects aimed at modernizing OCWD's in-house membrane pilots, trialing commercially in in-house RO online dashboards, and participates in AI research related to potable reuse. Alex Waite is the senior civil engineer for the City of Santa Monica's Water Resources Division. He oversees the design, construction, and optimization of the city's drinking water, wastewater, and recycled water systems to implement the city's goal of water self-sufficiency. He is also co-chair for the AWWA California-Nevada Section Recycled Water and Desalination Committee and vice president of the Water Reuse California Los Angeles chapter. Alex is a registered professional engineer in California and holds a bachelor's and master's degree in civil engineering from USC. Now, while there tends to be some rivalry with UCLA and USC, you won't find any of that here. Han and Alex have teamed up to give you a great update today and showcase Orange County Water District and City of Santa Monica's leadership in advancing the potable reuse and water industries. And with that, Han, I'll hand it over to you to get started.
Right, thank you very much, Meta. Let me get the presentation mode. Right, thank you very much, Meta, for the kind introduction. Good afternoon. My name is Han. I'm a senior scientist, process specialist from Orange County Water District. I'm really excited and happy and feel honored to join this webinar. So as Meta mentioned, we have 2 presentations. The unifying theme is squeezing the last drop using enhanced recovery RO to improve water production. So this is the webinar's plan. So I will talk first and talk about OCWD's pilot studies on 3 high recovery RO technology, and then Alex will take over and talk about the Santa Monica's pilot study and full-scale implementation on 1 high recovery RO technology, and we will end with the Q&A session. So this is the title of my presentation today. So I will share with you 3 piloting study using high recovery RO technology. They are the flow reversal RO or FRRO, closed circuit RO or CCRO, and then full osmosis RO or FORO. A brief outline of my presentation. I will provide some background information which will lead to the motivation for this work, which is to utilize high recovery RO to increase the recovery for high portable reuse application. I will go over each technology separately, and near the end, I will show you a table that summarizes the pros and cons of the 3 technology that we pilot tested and discuss preliminary cost comparison among the 3. So first, some background information. I think some of the audience here are familiar with reverse osmosis systems and processes. Conventional RO can remove dissolved solids, basically salt from the water, micromolecules and pathogens, but the recovery is still limited, mostly by mineral scaling in the feed water. If we're talking about portable reuse application, we can go up to 85% recovery on a 2 or 3 stage RO. This means 15% of the feed will become a concentrated waste stream. So for inland application, concentrate management and discharge is a real challenge. At R&D department, we have explored several high recovery RO technology in the past 5 or 6 years. I mentioned the CCRO, FORO, and FRRO pilot testing. So the goal here is to really test them out in pilot scale to make sure operationally they're feasible and also to see if they're economically viable on a larger scale. So closed circuit RO has been pilot tested at a number of utilities, including at Singapore Public Utility Board or PUB, Padre Dam, and LA County Sanitation District. The recovering range from 90 to 96%. Singapore PUB also tested flow reversal RO at a full scale in one of their new water facility from 2017 to 2022. They're able to increase their recovery from 75 to 90%. So the image on the upper right shows the Singapore retrofitted FRRO. So they didn't really build a new facility, but they modified the existing RO to implement flow reversal. And lastly, the city of Santa Monica has recently began testing the first municipal flow reversal RO at their full-scale facility. So Alex will talk about that in the second half of this webinar. So all pilot testing I will be mentioning today are completed at the Groundwater Replenishment System, or GWRS, at Orange County Water District. GWRS is currently the world's largest potable reuse facility. We can produce up to 130 mgd of highly purified water. We completed the final expansion of the GWRS in 2023. This is a joint project between OC Sanitation District and OCWD. So this simplified diagram shows the basic layout for the advanced water purification facility within the GWRS. So we're taking secondary wastewater effluents from OC Sanitation District from 2 plants about 174 mgd, and it will undergo a 3-step treatment process. First step is microfiltration, ultrafiltration. Second step is reverse osmosis, and then ultraviolet light with advanced oxidation or UV-AOP process. And after post-treatment, the final product water will go to our groundwater recharge basins in Anaheim and seawater intrusion barriers to prevent seawater intrusion. Focusing on the RO part, we have 27 5 mgd RO units. Each of them is a 3-stage RO running at 85% recovery. And the combined concentrated discharge is about 23 up to 23 mgd, and currently there is going to the Pacific Ocean. So what is the benefit of increasing recovery for the RO on GWRS? The most basic or most obvious reason is if we're able to increase the recovery, say from 85% to 91%, as shown in this diagram, we could generate more RO permeate. In this case, about 9 mgd more additional permeate, and at the same time, we could reduce the RO concentrate discharge by the same amount, so from 23 down to 14. There are also many other drivers for enhancing RO recovery. This include first, cost of imported water has been increasing steadily over the years, so the water resources has become really valuable. Secondly, water conservation method has reduced the source volume available for us to treat, so we have less wastewater to treat with. And thirdly, environmental stewardship. We don't want to discharge large volumes of highly concentrated brine into the environment. With that, I will go into the first technology I will cover today, which is called the flow reversal RO. So this is a continuous system utilizing conventional RO components, but there are 2 key features. The first one is called the fee-side flow reversal, or FR. So this diagram illustrates the basic concepts. Let me get my laser pointer out. So this is a RO pressure vessel. You can imagine there's RO membrane installed in series inside. So in a conventional RO configuration, the flow direction is fixed. So we always the water will go in from this side as undersaturated solution, and as the water move across the pressure vessel, it could get more and more concentrated. It will get more and more concentrated because we're removing a permeate. And near the exit region, mineral ions in the feed water could become supersaturated, so we could see mineral ions or crystals start to form on the membrane surface. This is due to the concentration polarization effect. So for flow reversal process, it's really simple. We're switching the flow direction periodically, so we will feed in from this side. We will use the undersaturated feed solution to dissolve or remove the crystal or scales already formed on the surface from the last cycle, and we're also reversing the concentration polarization profile. So for this project, we teamed up with a company called Rotec. They have this proprietary triggering system. It's based on the crystallization induction time estimate. So the definition of induction time is a time for a supersaturated solution to reach the onset nucleation. So we can run this process repeatedly, and then we can run a high recovery without the risk of scaling. The second feature is called block rotation. This simply means in a multi-stage RO system, the stage assignment for a particular pressure vessel blocks are not fixed. Sometime it will act as the first stage, sometime it will act as the third stage. So Alex will explain that a little bit in detail in his presentation. So this is the overview for the flow reversal pilot testing at Orange County. We conducted this between 2021 to 2023 in collaboration with Chart and Rotec. There's two phases to this pilot testing. Phase one, we're treating the AWPF RO feed water. We're simulating a full-scale retrofit of a conventional primary RO. In the second phase, we're treating the RO concentrate directly. We're simulating an RO brine concentrator. And because we completed phase one before the completion of the final expansion, the final expansion feed water actually changes. We have higher salinity in the feed, so we want to do a repeat. This is called the phase three, just to ensure that the pilot could keep the good performance and treat the final expansion feed water. So I included a photograph showing the pilot deployed in the AWPF RO building. This is a 30 GPM system, 3-stage RO, single pass. So this is the summary of finding for the flow reversal pilot study. In the first phase, the primary phase, we achieved 89 to 90% stable recovery. No additional chemical is needed. And you can see that here's a plot showing the normalized specific flux over about a 3-month runtime. This is a steady state trial. We keep the recovery at 90% recovery. The block rotation and flow reversal, it's about 40 minutes for the first and third stage. And for the second stage, the flow reversal occurs every 10 hours. So overall, you can see that the normalized specific flux, the overall specific flux declines about 23%. So overall, pretty stable. We also optimize the chemical cleaning, the recipe for that, and determine that a 3-month runtime between the chemical cleaning is most optimal. And this is in comparison with the full-scale RO CIP interval, which is about 6 to 12 months. We also completed the phase three after the final expansion water to ensure that the pilot could treat the final expansion feed water. Unfortunately, for the RO concentrated mode, it was not very successful. Basically, we were able to run to a recovery about 91% overall, but we determined the operation was not sustainable because of very heavy scaling, and the clean back was not very good after a CIP. So I will now talk about the second technology. This is called the closed circuit RO or CCRO. So this is a single stage RO, but it's a semi-batch process. So it's relying on complete recycling of the RO concentrate. Because this is a semi-batch process, there's 3 steps in the operation mode. In step 1, this is called the closed circuit mode. So we have in addition to conventional RO components, feed pump, high pressure pump, we also have this recirculation pump, and it will recirculate the RO concentrate back to the feed, 100% of the concentrate back to the feed. And at the same time, we're still producing permeate. So as you can imagine, as times went on, the water in this loop will become more and more concentrated, and the filtration time determine the volumetric recovery and the pressure in this loop. And at the bottom, we have a side conduit, which is just an empty pressure vessel holding, there's no membrane in there, it's just holding the fresh feed water from the previous cycle. In step 2, this is called the plug flow mode or purge mode. So at the end of a cycle, when the volumetric recovery reach the set point, the final concentrate will get pushed into the site conduit, and at the same time, the fresh feed will get pushed into the front of the pressure vessel holding the membranes. This is essentially a flushing step. And step 3 is called the site conduit refill mode. So we have a concentrate replacement pump that will activate and recharge the site conduit with fresh feed, and then it will discharge the final concentrate from the last cycle out of the pilot. So the key here is to maintain a good concentrate flushing efficiency. If we don't have that, we will have a scale or precursor of scale trapped in here, and it will from membrane really quickly for the next cycle. All right, so here are 2 photos showing the CCRO pilot deployed in the RO building. So we tested a DuPont reflex model. This is a 10 GPM system. You can see on the photo here, we have a pressure vessel on top holding the RO elements, and then at the bottom, we have the site conduit for the flushing purpose. So this pilot testing was completed between 2017 and 2019 in collaboration with DuPont and Jacobs. There's 2 phases. Phase 1, we're using the CCRO to treat the MF effluents, which is the same as RO feed water. This is simulating a full-scale CCRO as a primary RO, and we're filling the site conduit using the RO feed water from the plant. In phase 2, we're treating the RO concentrate directly. This is simulating a RO brine concentrator or 4-stage RO, and we're doing the flushing using both either the RO concentrate water or RO feed water from the plant. So here's the summary of the finding from this phase. In the primary mode, we achieve about 92% stable recovery. This is a plot showing the recovery, percentage recovery versus time. You can see the recovery is not constant in the CCRO. It's actually gradually increasing until it reached the maximum set point, which is 92% in this case, and then it will trigger the purge mode, and we will start the next cycle. So the filtration time is about 70 minutes, and you see the cyclic behavior for the CCRO. For the concentrator mode, we achieve about 91% overall recovery treating the RO concentrate. And experimentally, we determined that flushing the site conduit using the RO feed water extended the runtime between the CIPs by more than 2-fold. And then we also tested this so-called adaptive variable recovery mode to cope with fluctuating feed water quality. So I have this diagram to illustrate this concept. So in here, we have a plot of electroconductivity of the RO concentrate coming into the pilot. This is represented in the red curve. So in this case, we're not running the CCRO at a constant maximum recovery, but instead, we're using a maximum EC trigger. So the concept is the CCRO will change its recovery based on the feed water quality. So with this, it can improve the system performance. And lastly, we determine optimum runtime between the CIP is about 2 months for this pilot. Okay, I will move on to the third technology I will cover today. This is called the full osmosis RO. So this is different from the previous 2. This is a hybrid membrane system because we have a FO membrane in front coupled with the RO membrane. This is a double barrier system, 1 pass. The key here is to maintain a draw solution loop. So the draw solution is sodium chloride in this case. And the FO membrane looks like this. This is a flat sheet membrane stacked on top of each other to form a membrane module. So the feed water here is the RO concentrate coming from the GWRS. So when the feed come in, it will get in contact with the FO membrane and at the same time get in contact with the regenerated draw solution. Because of natural osmotic pressure differences, we will see a flux, water flux moving from this direction to this. This is causing a producing a diluted draw solution, and at the same time, we're creating a concentrate reject, which contain the contaminant removed from the RO concentrate. And the RO will regenerate the draw solution. It will produce a final permeate, and this will loop back and link with the FO. One of the unique feature here is the salt concentration in the draw solution loop is retained within the closed loop. So here are two photos showing the pilot deployed in the AWPF RO building. We have this 1 GPM system from Peripheral. It's much smaller than the other two pilots. You see the two FO modules here. They're running in parallel, and the draw solution makeup tank. And we have the control system here. And behind the pilot, this is a side view. You can see a pair of seawater elements, RO elements. This is for the draw solution regeneration. Okay, so this slide summarizes the basic finding for the FORO pilot study. We're able to treat the RO concentrate directly, and the FORO system was able to run to about 35% recovery. This is equivalent to about 90.3% overall recovery. The FO CIP frequency is about 3 to 4 weeks. The RO CIP interval is about every 6 months. We do encounter a number of operational challenges in this pilot study. First one is a pretty severe organic fouling and silica scaling of the FO membrane. So that's why we need to clean it very often, less than a month. And then we also observe some FO membrane integrity issue. This is mainly due to if we have a pressure swing upstream, that will translate into the FO membrane, and sometimes we see membrane delamination problems. And thirdly, we have some mechanical issue with a pressure relief valve, and that caused some draw solution bleed. So we need to add a lot of salt to make up the salt loss in this case. So for the CCRO and FORO pilot study, we also asked our partner Corollo engineers to come up with a 10 and 20 MGD full-scale system design and preliminary cost estimate. I will not go into the detail here, but the conclusion is if we're looking at the combined unit cost of building either a 10 or 20 MGD system using either technology, the cost is quite similar. So we're talking about $1,100 to about $1,400 per acre foot. And then this is because the CCRO actually have higher capital costs, but has lower annual operation and maintenance costs. And the flow, for osmosis RO system has the reverse trend. So for the flow reversal retrofit, we did our in-house estimate using OCWD site-specific cost number. Here we're looking at 3 cases. First one is if we have a conventional RO if we build a conventional RO system, the unit capital cost is about $90 per acre foot. If we doing a retrofit on an existing RO system and get the recovery up to 90%, we will be generating only about 0.28 MGD additional permeate. So the unit capital cost is about $621 there. And the third case is so-called melted rate. So if you're looking at the RO units plus the retrofit cost, and because we need to divide that by the 5.28 MGD, so that cost come out to be $118 per acre foot. Similarly, we can look at the unit operation and maintenance costs. So for the conventional RO units, about $99 per acre foot. So for the retrofit, we need to spend about $16 more per acre foot because we need to account for more frequent chemical cleaning and higher electrical power consumption due to membrane fouling. If we look at the combined cost, we're talking about $637 as the combined cost for the generating the additional water. Another interesting observation we see during this cost estimate is if we're able to increase the recovery, maybe by just 1%, from 90% to 91%, we can reduce the unit capital cost greatly. So about down to $471. This is because we're able to generate more permeate if we're able to increase the recovery. So the message here is if there is advancement in the flow reversal technology or better anti-scaling or better membrane performance that will lead to increased recovery, the unit capital cost will greatly reduce. So basically, we can squeeze out the last drop of the water here. Okay, so in conclusion, I want to show you this table that summarizes the relative pros and cons of the 3 recovery technology, high recovery technology, RO technology. The first one, the flow reversal RO. The pros are it's able to retrofit of a existing RO. The CIP interval is about 3 months, and the salt and organic rejection are very similar to a conventional RO. The disadvantage are the concentrator mode was not successful. And then we also see some recovery reduction during the transitional period. Also overall, we're losing about 1%. So the primary RO mode tested achieved about 89 to 90% overall recovery. For the closed circuit RO, it worked well in both primary mode and concentrator mode. We also test out this adaptive approach to cope with feedwater fluctuation quality. And then the cons are the concentrator mode require RO feedwater for the side conduit flushing. So we need to push the system harder to compensate for the loss. And then the permeate quality vary with time. So the permeate quality actually also have this cyclic behavior. We're able to get 92% for the primary mode and achieve 91% for the concentrator mode for the CCRO. And lastly, for the full osmosis RO, the internal salt retention minimized the concentrate reject salinity. It also had better organic virus rejection than the CCRO. Some of the negatives are the CIP interval is pretty short, and we also observe some membrane integrity issue and high draw solution usage. So overall, the concentrator mode achieved about 89.5 to 90.3% overall recovery. Two other important conclusion is the unit cost for additional permeate from a full-scale flow reversal retrofit is lower than both the CCRO and FORO system. If we're able to increase the recovery a little bit more, the dollar per acre foot will drop greatly. And then I want to mention that all three pilots actually produce high quality permeate that could be blended with the existing primary RO permeate to increase the overall production. So with that, I want to acknowledge the OCWD research team and our industrial collaborator and funding agencies. So thank you very much. I will turn it over to Alex to talk about the full-scale implementation for the flow reversal system.
Awesome. Thank you so much, Juan, for the great presentation. And thank you, Orange County Water District, for the opportunity to co-present today on the efforts that Santa Monica has been up to with respect to enhanced recovery RO and trying to squeeze out that last drop. There we go. Okay, so before we dig into the enhanced recovery RO processes that were pilot tested and actually implemented at the full scale solution, let's actually dig into the context of why we investigated it in the first place. So at Santa Monica, we've been working since 2018 to become self-sufficient on local water supplies. And we identified 3 reasons why that was critical to the city of Santa Monica. So first, by implementing these local water supplies, we're creating a diverse, sustainable, and drought resilient supply that can support the sustainable community of Santa Monica. Second, these local water supplies can reduce our energy footprint overall and then support our carbon reduction goals for the city, which you can see on the right-hand side in our climate action and adaptation plan. Third, and finally, it's long-term cost benefits for our ratepayers. Comparing the cost of local resources, like improving the efficiencies of our existing groundwater desalter facility, have long-term cost benefits compared to other sources like imported water. And so one of the projects that was identified in that 2018 Sustainable Water Master Plan was the Olympic Wellfield Restoration and Arcadia Water Treatment Plant Production Expansion Project. The Arcadia Water Treatment Plant is a groundwater desalting facility that was constructed in 2010 with a 10 MGD capacity. And we are wrapping up construction for upgrades to this facility to include first UV, AOP, and GAC pretreatment system for the Olympic wellfield, which was contaminated with historical contaminants like 1,4-dioxane, TC, and PC. That water is then blended with our existing water treatment system. And the second part of the project is actually expanding our reverse osmosis system to retrofit to a higher recovery, enhanced recovery process that can achieve greater than 90% recovery. Right now we're at about 82, 83%, and now we're looking at 90% or more. And also finally expanding the total capacity of the facility from 10 MGD to 13 MGD. So we looked at, well, is the concentrate actually worth the squeeze? Is there any benefit for us to investigate these technologies any further and see if we can improve our local water resources? So back in 2010, we investigated pilot studies for closed circuit RO and the flow reversal RO. Closed circuit provided by Desaltec, now DuPont, and the flow reversal RO by Rotec. And we did a side-by-side pilot test of these different technologies and comparing against the existing RO system, which is a 1900 GPM feed capacity system, a three-stage system, as I mentioned, going around 83 up to a maximum of 85%. But before I dig into the results of the pilot test, so Han did a great presentation covering how the flow reversal RO process worked. Just one additional step that was mentioned was the multi-stage block rotation process. So in the flow reversal process, it's actually set up in a series of blocks, and those blocks are cycled through a rotation where each block in the first and third stage are taking turns as that next system. So as the induction timer is about to be reached, the last stage will actually rotate back to the first stage, and a new first stage block will rotate into third stage. And so this reversal process, coupled with the flow direction switch, will feed undersaturated feed water into this vessel that was seeing some pretty aggressive water and dissolve those scale particulates before they start proliferating. So those two processes together are able to not just meet an existing recovery, but push the recovery well beyond what a conventional system is able to accomplish. Well, let's dig into the pilot summary now, looking at the flow reversal RO versus the CCRO. So this slide is showing the recoveries of the two systems, as well as the dashed line showing intervals for CIPs, and then the triangles are showing the membrane replacements. And so what we see is that for the flow reversal process, we were able to achieve some pretty sustained operations at higher recovery at 88% or greater. For the CCRO, we were unable to achieve those target recoveries, and ultimately we ceased operations on that pilot in early September of 2020. And here's a table kind of summarizing the performance of both of those systems. Some key things to point out for the flow reversal process, that we had a total online time of over 140 days, with 106 days at 89% or greater recovery. And we also had 5 CIPs during that pilot, so it was about a CIP about once a month, and those membranes were never replaced. And compared against the CCRO, we had 3 CIPs and several membrane replacements. And so these pilot results then fed into what we could look at a full-scale system. And so the next step of this was looking at, well, what's the cost competitiveness of flow reversal RO versus closed circuit RO versus the cost of imported water. And so we did this side-by-side analysis, and what we found is that for retrofitting the existing 4 RO trains, our cost was about $1,070 per acre foot for retrofitting all 4 of our conventional RO trains. Now compare that against the cost of imported water at 2018 rates, and they're actually pretty competitive, right? Then you compare that against the cost of a brand new FRO skid, and that's a significantly additional cost. And then comparing again against 2 closed circuit RO trains, and the cost is even higher. So again, showing that the cost for the flow reversal retrofit is very cost advantageous for us. And so you put all this together, the results that we had from the pilot testing and the cost benefit analysis, and there are several benefits for Santa Monica to pursue full-scale implementation of the flow reversal RO retrofit. So first, we saw those stable operations at high recovery at 90% or more. We have the ability to retrofit existing RO skids, so we have an existing asset and we can retrofit it in place without building new capacity or a new facility, so that will lower our overall capital costs. There's a lower operation and lifecycle costs with the flow reversal RO compared to the CCRO when looking at the energy and chemical consumption, and also the CIP frequency. We have funding flexibilities. So for example, since we're retrofitting an existing system rather than building on a brand new system, in the instance like we had in COVID where funding became very tight, we actually had the flexibility to look at retrofitting maybe 1 out of the 4 trains, or maybe 2 out of the 4 trains, and wait to see where the funding comes back in. Luckily, through our funding partners, we didn't have to go that route. We were able to do all 4 simultaneously, but at least we had that flexibility, right? We also have the operational flexibility. So in the event that flow reversal just isn't working for whatever reason, it still is a conventional RO system. You can turn off the flow reversal mode, go back to the 82, 83% recovery, and continue operating. So you don't have a stranded asset. And so with all those things in mind, it overall builds into a relatively lower risk profile for the flow reversal process compared to a CCRO process for us in Santa Monica. And so culminating that this is actually the first municipal application of flow reversal reverse osmosis in the United States. So we're very proud to have the first municipal application for this project. All right, so now we're digging into the full-scale implementation. And so we started construction on this project at the beginning of 2022. And since that time, we've done a lot of work on site, including the new UVOP process, but also the retrofit of these 4 skids, which have now actually been operating for about 9 months. So we just want to walk through what the retrofit looks like. So the picture on the left-hand side is showing the conventional system. So it's a 3-stage array operating at 83% recovery. So what this retrofit looks like is taking this first block that was first stage, and now this is our first/third stage block rotation group. We have the middle, which is second stage and has now been retrofitted again to second stage, but with the ability to reverse flow back and forth. And then since this is a retrofit of an existing skid, we have to work within the hydraulics of the existing system. And so there was this block of vessels, about 10 vessels, what actually was very complicated to try and bring that into the flow reversal process, but really critical to maintain an overall average flux rate of about 13 GFD. So instead of trying to finagle that way into the retrofit process, instead this became a static set of vessels. And so now we have a control group to compare against the blocks that are constantly rotating. And so on the picture on the right-hand side is showing the completed retrofit, now with a few more vessels, but overall utilizing exactly the same vessels, a lot of the existing piping, but replaced with some new piping in certain locations and also additional valves, pumps, and control systems. So this is a summary of those changes from the conventional system to the flow reversal RO. One of the key features I want to point out is with respect to the membrane. So we were using the Toray TMG membrane, 440 square foot membrane. For the retrofit, we're actually using the same membrane, but now with a split ring brine seal. And so what the split ring allows is for water to actually flow back and forth in the vessel and still block water from impeding onto the next vessel in the process. So it's a really neat design. It's a really simple seal. And as I mentioned, there's a lot of additional valves, additional booster pump, some additional controls and instrumentation in order to facilitate this fully automatic process in terms of the reversal process. So I want to show a schematic here of what that transition process looks like in this retrofitted system. So this diagram is showing right now we have these 14 blocks A through N. In this case, the ones in red, those are our third stage. So blocks B, C, and N are operating in third stage. And as it goes through this fully automatic process, we have new blocks that are rotating out of first stage into third stage. The second stage is isolating and then flowing back and forth. The existing third stage are now being brought back into first stage. And now the system stabilizes and begin operations. And this in the data looks like the first stage booster pump is really providing the majority of the pressure through the reversal process. So it's operating in a plug flow mode, and then everything starts to slow down in order to facilitate those valve closures so we don't hammer our system with a water hammer. So we're utilizing the first stage booster pump to push water through the process while the rest of it is being isolated. And then in terms of the recovery, we're seeing a slight recovery drop during this transition process. So it's going maybe from 90% recovery overall to about 75, 76% during that transition phase. It takes about 36 hours to fully cycle through the entire process. So in that previous example, we had blocks B, C, and N, and second stage going into the page. So to rotate through all the blocks in every configuration to get back there, it takes about 36 hours. And so we have that 90% recovery in plug flow mode, short transition step. But what this means is that the total recovery for this entire 36 hours is actually around 89.1% when you factor in all this time for the reversal process. So that's an important piece, and that's something that we're continuing to investigate of how we can further optimize this to bring our total recovery over the 36 hours up a little bit higher. And I'll mention a couple things we're looking at the end of the presentation. All right, let's dig into some of the data and lessons learned. this is what the data looks like for the full-scale system. And so you see the cyclical process as the process is changing from one third stage block to another. The important piece to focus in on, though, is the space in between those reversals. And so that's when we're operating a plug flow mode. And that's, you know, just like the same data that you see at a conventional system, just with these hour transitions in the middle. Another important piece for Santa Monica, as I mentioned, is that energy footprint. And so what we found on the full scale system is that our specific energy consumption compared to conventional is actually significantly lower than the conventional system, even when operating at the higher recovery. And so this is showing data for one of our skids that was operating from October to December. So even at the 90% recovery, we're seeing great SEC. But unfortunately, at the end of December, there was a CIP that was conducted, a clean in place, and it was actually an incomplete CIP, and it led to fouling occurring in this train. And since that point, the performance has declined, and although we've done several CIPs, it really hasn't gotten to where we were expecting to be. So it shows that, you know, this process, although, you know, it operates at that higher recovery, you know, with there is still the possibility for scale to form, and especially if you're introducing the opportunity for scale to form through an incomplete CIP process, it really can escalate the process even further. So what have we done to look into this? Well, on closer inspection, we found that we actually had a lot of scale in our system. And what you're seeing here is almost 100% calcium carbonate scale. In the middle picture is a flow meter. We have a pump on the right-hand side. And so this has a lot of impacts on the process as it moves forward. And so we looked at several different methods to prevent this scale formation. We did several of these, including increasing the RO feed anti-scalant dose for the Vitek 4000. And then we ultimately looked at, well, let's try and change the anti-scalant. Let's try and change the pre-treatment to improve the process. And so we did a test where we used the AWC A119 product on one of our RO skids for about a month and compared that to another skid that was previously using the Vitek 4000. And what we found is actually a really significant improvement in the performance using the AWC product for this particular application. And it ultimately was about we estimated it's a savings of about $88,000 annually with this AWC versus the Vista product. And the savings is not coming from the anti-scalant dose, it's actually coming from a increase in the pH set point. So we're using less sulfuric acid to depress that pH. So this is a point that the pre-treatment to the process is really just as important as the high recovery process itself. So if you have adequate pre-treatment, especially for these enhanced RO performance set points, 90% or more with some pretty significant scale factors like alkalinity or silica, then pre-treatment is really critical. And when we took apart this process, unlike on the previous anti-scalant, totally clean. And we've taken it apart several times since that point in June. Again, it's totally clean. So again, the pre-treatment is really critical to this process. So I have a few more design considerations for folks who are considering these high recovery RO processes. When looking at the flow reversal process, there are a lot of pneumatic valves, about 56 2 and 2.5 inch pneumatic valves on each train. So that's a lot of equipment that needs a preventative maintenance schedule to check that everything is working perfectly. The valves are closing within an 8 to 10 second time period, so you're not creating a water hammer. So it's very important to the process. Also maintaining a higher pneumatic air pressure. When we started the process, we were operating a little bit lower air pressure, but with such a big system and so many valves, you really need maybe a higher air pressure than you might think when you start. And so that's just another piece to keep in mind. Also setting your shims. So proper membrane loading is super critical with a process where you can send water not just one way, but now the other way. You have a situation called racking, and your membrane might actually rack in the process if it's not shimmed correctly. So setting those membranes and shimming is really critical. And the last thing I just want to say is the retrofit versus new skid. So with a retrofit, you are utilizing a lot of the existing hydraulic conditions that you have in your existing system. And there may be some disadvantages to that versus rebuilding with a new skid with something that can be completely controlled by the manufacturer versus working within an existing boundary. Last things I want to say in terms of construction and commissioning considerations. So this is something we learned through the process is the considerations of a general contractor working on a project like this versus an OEM procurement and construction. With a general contractor who may not be familiar with a high recovery process like flow reversal RO, there was quite a bit of learning time that came into the construction process. And so something we would consider and hope all of you would consider too is maybe looking to see if there's an OEM procurement process to facilitate your experience versus having a GC do it. And eventually they were able to get up to speed and it sped up the process quite a bit, but it did take a little bit more time than was expected. We also recommend building in extra unknowns, especially for a retrofit. There's so many things that you don't know until you get out there and you try and plug in the theory, and then you actually see the hydraulics of the process and things that you thought were true in the pilot and they didn't pan out in the full scale. So that's an important piece, is build in that extra time. There's also no there's also no increase, no 0 to 100 in recovery. Stepwise increases in that recovery, 82, 85, 88, and so on, gives you time to assess at each step if everything is working as you expected before you make the next step where you could actually potentially cause irreversible fouling. And the last thing I would say is to lock in your performance guarantee. And so you could ask for everything under the sun for the process to work perfectly, but all of that comes at a cost. So there needs to be a compromise on what the expectations are in terms of delivering a system like this and what RO feed water quality is expected to then set what the performance in the finished water quality will look like. So for example, for Santa Monica, the performance guarantee was a minimum of 90% recovery in the flow reversal mode with a CAP interval of every 60 days. So what are our next steps for this project? So we're finalizing the permit amendment for the Olympic wellfield restoration. We're continuing a 2-month full-scale contractual testing period to prove out the performance guarantee that I just mentioned. And then we're looking to optimize that flow reversal transition process to increase that overall recovery to get greater than the 89.1 that I mentioned earlier. And so some of the ways that we're thinking about this is potentially that second stage rotation, instead of occurring every cycle, maybe every other cycle, every 4 cycles, maybe there's a better time frame to increase recovery there. Decreasing valve closure times to give us a little bit less time in transition, a little bit more in plug flow mode. And then also just increasing the plug flow mode duration. Right now it's at 1 hour, maybe we could look at 1 hour and 10, hour and 15. So on every little bit will get us a little bit more water production in the end. Just want to acknowledge all of our regulatory and funding partners, including Department of Water Resources, the Metropolitan Water District of Southern California, the design build team led by Walsh Construction and Brown and Caldwell Design Engineer, GHD as our owner's engineer, and several other teams to facilitate other aspects of the project. So thank you all very much for your time, and I look forward to your questions.
Awesome. Thank you so much, Alex and Han. Thank you for closing us out, Alex, for the second half. And Han, you gave an amazing presentation on really setting the context to this technology that we see is being implemented here in Santa Monica. I'd love to invite you both back on camera for the Q&A, and we'll just kind of tackle these as we see them. I do want to, 1 second, I think I have to bring Han back on. Hopefully that worked. Thank you. I do also want to encourage folks to go ahead and submit any questions you see you have in the Q&A box. If you think of something after the webinar, or if we're not able to get back to you live during the time that we have here, we will circle back with you. So please do include your name and email address if you can, and we'll be sure to circle back with you after. So I'll start with you, Han. I believe this was asked during your portion of the presentation. Have you estimated the CCRO recovery of the post-expansion RO feed water?
No, because the CCRO project was completed before the completion of the final expansion. Yeah, so if we want to determine that, we have to run some additional tests. Yeah.
Thank you, Han. Alex, we've got a couple of questions your way. During CIPs for FRRO, do you only clean the stage 1 and 3 system and not stage 2?
Sure. So for the pilot scale, the entire system undergoes a CIP simultaneously. For the full scale system, we have the ability to segment the process. So we will do a CIP on half of the first third blocks, the second half of the first third blocks, and then the second stage completely independently from the rest of the system.
Thank you, Alex. And speaking of the pilot, we do have a question about that. Someone has commented that they did read your pilot paper and are asking, did it operate more effectively than the full scale for some reason?
So part of the process there is that the closure times in terms of the valves was also a little bit shorter in the pilot. It is a smaller system, and so you have smaller valves that can close a little bit more rapidly, and so that actually shortens your transition time. In the pilot, we were also transitioning the second stage every other cycle versus the full scale right now is flipping back and forth every cycle. So that is something that we are looking to investigate for the full scale system of maybe there's an opportunity to take that second stage and maybe do it every other cycle instead of what's currently happening as every cycle. So you are correct. It is a slight change. I think it's like 0.1%, but I think there's a lot of ways that we can continue optimizing the full scale system.
Thank you. Next question. Have similar cost estimates been performed recently since the CCRO technology no longer needs a side conduit when treating brine directly at the about 40 to 60% range recovery?
I'm not 100% sure, but I think the side conduit is there to basically prolong the flushing, so to make the flushing more effective. So I haven't heard that they totally eliminate that. Yeah, so I have to get more information to answer that. But I think through modeling, you should be able to estimate what is the cost if there is no side conduit.
If I could jump in as well, so the C0 pilot system that Santa Monica operated was exactly the same one as what was operated at OCWD. And so we also had that side conduit there. Now, our understanding is that that side conduit is really necessary when you start looking at super low recoveries. So I think it was around 40% or lower. And in a concentrator mode, that may be really important, right? Because you have a pretty high feed stream and you need to cycle through that as fast as possible. But in terms of higher recovery modes, we were not at that, we were not below that threshold. And so, that is something that we could have looked at is operating without that side conduit. But for the purposes of the pilot, it was operated in that configuration.
Thank you. And I think this question might be for the both of you, if you could provide some insight. And it relates to a question that we also received during registration. So I'm going to kind of beam them up together. I realize the wastewater reduces material. Do you have any concerns about microplastics? And then it sort of falls into this theme of what is the impact of RO waste on the environment?
So I can start with that. In terms of, I'll say on the groundwater side, we don't have the issue of microplastics in our groundwater supply, which is great. But we do also operate our sustainable water infrastructure project, which is a recycled water facility, very similar to GWRS. And so microplastics are a concern in the feed stream to the facility in the raw wastewater. That is a constituent of emerging concern that we are looking at. However, based off of the literature reviews and investigations done so far, the advanced treatment processes within our RO process, and I'm sure it'd be the same at GWRS, are excellent in removing those microplastics, those harmful contaminants from the raw sources. Now, the membranes themselves, in terms of contributing to those microplastics, that is something I'm not as familiar with, and would definitely have to read up on that to get back to you a little bit more detail.
Thank you, Alex. Can you elaborate on the reason why the CCRO membranes needed to be replaced 3 times? I believe that was something you were talking about, Alex.
Yeah, so the quick reason why is that it's a lot faster to replace membranes than it is to do a clean in place. So clean in place could take a whole day or more, depending on which chemicals you're using. To replace membranes can take, less than an hour. So that was the rationale, as we had the ability to use membranes at a relatively faster pace, and so that was the purpose there. It wasn't 100% necessary, maybe not, but we had the ability to get back into production faster than if we were doing a CIP.
Thank you, Alex. Han, this may have been an observation in OCWD study. The question is there any reduction in membrane lifespan using FRRO?
We haven't seen that. The only thing I can mention is for the concentrator mode, it didn't really work out. So we actually need to change the membrane after the concentrator mode because we couldn't really clean the membrane back. But for the primary mode, it's mostly successful. We conducted about 8 CIPs, and each of them kind of after that we can still restore most of the specific flux and the rejection. So perhaps we need to basically run it even longer to determine that if there's any negative impact on the membrane life. Yeah.
Thank you, Han. This question, that admits this may have been in the presentation, but how was the switch, how was switch one and Defcolent to another? And was that change due to concentration changes, or was it a different combination of chemicals?
Sorry, I'm not quite sure I understand that. Was the question asking about changing antiscalants?
Yeah,
Yes.
probably
Okay.
yes. Yeah.
Okay.
Okay. Yeah, how was it? So the actual cleaning out CIP chemical, or excuse me, cleaning out antiscalant. So, we had to drain out the whole tank and clean it. So it's kind of a pain. You have to, bring in hazardous waste to dispose of that material. But in terms of the operational changes, we really saw kind of an immediate change in performance on the one skid that we were testing on, which was effectively, fresh set of membranes, had never seen the original Avista product. So on the A to C product, it performed, about 20 to 30 PSI feed pressure lower beginning than on the other antiscalant. And so that was quite an improvement compared to our other RO skids that were operating on the previous system. And so I do just want to say that it doesn't mean that one is necessarily always going to be better than the other. It just means that for this particular application, we have high silica content, high alkalinity content, and so this particular antiscalant chemistry with the AWC product works really well for us at this higher recovery mode. That may not be the case in a potable reuse facility like in Han's facility with GWRS, or even another brackish desalter.
Thank you so much, Alex. I appreciate that. There was one question that I want to kind of end on here that was asked during the registration process, and I'd love both of your perspectives and comments about this. How does a project like this really support each of your agencies' water supply portfolio, and particularly when we're talking about potable reuse and imported water?
I can start. So basically, the goal here is to because I mentioned we're facing reduced amount of wastewater to treat with. OC San was able to deliver a maximum about 174 MGD, but sometimes because of equipment issue, we have reduced flow. So we need to have some sort of strategy to make sure we can maintain the product, basically the permeate production. So one way to do that is try to increase the recovery to basically squeeze it more out, so we can have more basically tools in our pocket to solve this problem. Yeah.
Mm-hmm. Yeah, and exactly like what Han is saying is on the groundwater side, groundwater is not an infinite source. It has a limit. And for some who may be familiar with the Sustainable Groundwater Management Act, so now there's actually state hard limits in terms of groundwater sources, including in the Santa Monica groundwater basin. So it means we cannot just continue to pump as much water out as we want. And so these enhanced recovery technologies like the flow reversal RO process, it will allow us to increase our overall production without actually pumping more water out of the ground. So we're actually able to produce about 1,200 acre feet more per year without actually pumping any more groundwater out. That's hugely advantageous for us to be much more sustainable and more resilient with our finite water supplies.
Oh, that's amazing. Thank you so much, Alex and Han. I just want to thank you both again as we close out the webinar here for your great presentations today, your great commentary to close this out here. And I want to thank all our attendees for joining us today and remind folks that this webinar is being recorded. It will be available to share afterwards, and I'll sort of end on this screen here. If you have any questions, think about anything after the fact, Alex and Han did share their contact information, so please feel free to reach out to them, or you could always email Orange County Water District at info@ocwd.com, and we'll field those questions over to our speakers today. So thank you all very much. I appreciate it, and have a good rest of your day.
Great. Thank you all.
Bye.
Thank you for your
Thank you, Meta,
time.
for hosting. Yep, thank you.